Hello everyone. Today let's discuss about the topological sorting. So here let me give topological sorting, right? I'll just give here topological sorting. So what is mainly topological sorting? Here let's see. Let's try to understand the approach first. Topological sorting is used in, I'll just give here, topological sorting is used in directed acyclic graphs. Nothing but we will call this one as DAG, right? So we'll be making use of the topological sorting in directed acyclic graph to arrange the vertices in a linear order. So to arrange this one vertices in a linear order, we'll be making use of topological sorting. So let's see how we will arrange this one in the linear order. So topological sorting is used in directed acyclic graph, nothing but DAG, to arrange the vertices in a linear order such that every directed edge U, if this has to be every directed edge U, U has to be V, nothing but vertex U must come before the vertex V, always. So vertex U must always come before the vertex V in the ordering. That's what we have to make sure. So mainly topological sorting is used in directed acyclic graphs to arrange the vertices in the linear order, this one, and we will make sure that every vertex V, vertex U must come before the vertex V in the ordering. Basically, what does the algorithm involve? Algorithm involves performing a DFS. So we will perform DFS here on the graph and using a stack to store the vertices in post order. So we'll be making use of the DFS on the graph and we will make use of the stack to store the vertices in the post order. So then the stack is then reversed to get the topological order. So finally what we will do, we will reverse the stack, this one. We will be reversing the stack to get the topological order. I hope this is completely clear. So this is the approach that we'll be going with. Let's write the code and try to understand this one with the example, and finally we will discuss about the time complexity as well as the space complexity. So initially let's write the function to perform the topological sorting. I'll just give here function. So here let me make this one topological sorting up. Let me take the parameters vertices and adjacent list. So initially what we will do, we will create the visited array to keep track of the visited vertices. So what are all the vertices that are visited, we have to track that one, right? So for that purpose we will create the visited array. So I'll just give here visited. Let's initialize the array of size V and let's fill this one initially with the boolean value false. So let's also initialize the stack to store the topological order. So finally we will be reversing the stack to get the topological order, right? So we have to store the topological order somewhere. So for that purpose we'll be initializing the stack as we had discussed in the approach. So I'll just come here and let me consider this one. So here next let's make use of the helper function or the inner function to perform DFS. So as we had discussed in this one approach, we'll be performing the DFS, right? So DFS of the parameter, I just take V here. Let's mark the current vertex as visited. So whatever the current vertex that has been visited, we will mark that one as visited. Nothing but I'll be giving the boolean value true over here. Next, after the initialization, let's move on with the iteration. Nothing but we will visit all the neighbors of the current vertex and mark them. If the neighbor has not been visited, then we will recursively visit it. And finally, we'll push the vertex to the stack after visiting all its neighbors. That's what we'll be doing here. First step, let's visit all the neighbors of the current vertex. So I'll just consider neighbor of adjacency list. Within the array, I'll just consider V. So if the neighbor has not been visited yet, we will recursively visit this one. I can just write visited of neighbor equals undefined, or let me write in this way. If not of visited neighbor. Means if the neighbor has not been visited, we have to recursively visit it, right? So let me make use of the recursive function dfs of neighbor. So I hope this is clear. So finally what we will do, here, did I miss something here? Just give me a second here. No, let's push the current vertex to the stack after visiting all the neighbors, all its neighbors. Sorry, I'll just make use of the push of v, right? We have considered a parameter. So I hope this is clear. Next step is we have to perform the DFS for each vertex in the graph. So we have done only for the one vertex, initial vertex, and that's what we have done here by considering the DFS, and we have performed this one, right? DFS and this one. We have marked this one, and finally we have what we have done. We have pushed the current vertex to the stack after visiting all its neighbors. So we have to perform the DFS for all the vertex, right? For each vertex in the graph. For that, I'll just be making use of this one, for loop. So let I equal 0, I less than v. So I hope this is clear. If the vertex, same step, if the vertex has not been visited, we will call the DFS function again. So here I'll just consider this one, visited of iterated value of not of visited of I. Then I can just call the DFS function in this way, DFS of I. Same thing. So finally here, for the current vertex we did, so for each vertex we have to do, every vertex we have to check, right? For that purpose, we are performing this iteration mainly. So finally, we will, as we had discussed in the approach, we will be reversing the stack to get the topological, this one, topological order. So I'll just return here stack dot reverse. So I have to reverse this one, right? So I hope this is clear till here. So let me consider the example. By considering example, you'll get to know. Then we'll finally discuss about the time complexity as well as the space complexity. So I'll just come here. Let me paste the example here. So I have considered the number of vertices 6. So as this is 0 based vertices, we have considered the vertex from 0, right? This is 0 based. So number of vertices we have considered 6, 0, 2, 3, this one at vertex 0, 3, 4 at vertex 1. This one nothing but this is adjacency list for all the vertex, right? Starting from the vertex 0 to vertex 5. Nothing but we are having the vertices 6 vertices, right? So here you can see what I have done. Then I have just considered the order, and I have given here topological sort of, I have just called the function over here. In this step, we are calling the function. What are the parameters? B and the adjacency list, right? So that we have considered within the function. Finally, we are printing the topological order. So here, let's run this. I hope we get the correct solution. So topological sort is not defined. Line number 32. So here this has to be topological sorting. Just give me a second. We have considered topological sorting here, right? This one, function name. Let me run this one again. So here you can clearly see topological order is 1, 0, 3, 4, 2, 5. So this works absolutely correct. So then what we'll be doing finally, so what's the time complexity and the space complexity? So overall time complexity would be big O of V plus E. We know that V is nothing but the number of vertices and E is nothing but the number of edges. So the overall time complexity would be big O of V plus E, and the overall space complexity would be big O of V. Nothing but we are making use of big O of, we are visiting the array and stack, right? Once. So it will be big O of V. So finally, I'll just give here time complexity will be big O of V plus E, and the space complexity would be big O of V here. I hope this is clear. So this is it. Next, let's discuss about the Euclidean algorithm to find the GCD. So for now, this is it. Thanks for watching, guys.